Well, welcome back. This is our video series on exponential functions. This is part 2, and it's the second day on section 10-1. Today we're going to learn how to write an exponential function of this form that we know, y equals a times b to the x. We're going to write an exponential function. Let's review again what that means here. Okay. X is, of course, the x-axis, and a lot of times we refer to that as time. And, of course, the y is the y-axis. A is our y-intercept, so that would be a point on the y-axis. Now, remember, it's called the initial amount on the y-axis because that initially is now. It's where x is 0, this is the now. If you went into the future, that would be like going to the right on the graph here. And if we went to the left, that's like going into the past. Okay? So this point that's on the y-axis here is called the y-intercept, or a. This point has the ordered pair right here, has the ordered pair 0, some a value, some a. And then we don't know the rate here right now, but if we have an intercept, a y-intercept, we're going to use that information to help us find the equation. Let's start with, let's say we begin with a point 0, 3. Now that's the y-intercept because it's got that ordered pair 0, 3. And another point, let's say negative 1, 6. Well, I could put that on the graph here. I don't need to, but negative 1, 6 has got to be, let's say that this is 0, 3. And let's say this other point is at negative 1, 6. We don't actually need to graph it here, but I'm going to do that anyway. And I can see by looking at this that the graph looks like it's going to decline or decay. And that means that because it's decaying, I should expect to get a base that is between 0 and 1. Remember, the bases between 0 and 1 are decay. It should be going downhill. Well, what we're going to do is we're going to put this value in for a, and these two values happen to be x and y. We're going to stick those in there as well. So the y value here is 6, a is 3. We don't know the base, but we know x is a negative 1. Now to solve this, we need to find b. We're going to solve this by starting by dividing by the a value, in this case 3. We always start that way by getting this divided by the a value. So we get 2 equals b to the negative 1. Well, we need to get b alone, but it's not. So let's change this by knowing that negative exponents cause me to flip it over, reciprocal, and raise it to the 1 power. Now to get b up here on the top where it belongs, we're going to need to cross multiply. So 2 times b is 2b, and 1 times 1 is 1. And divide both sides by 2, and we discover that b equals 1/2. Well, that's what we figured. This looks like it's a fraction between 0 and 1. It's decay. So we know that our equation is going to be y equals the y-intercept of 3, a base of 1/2, and the exponent is x. Now this is what we're going to do today. We're going to practice writing equations given a point. And the points you're going to be given are points that are y-intercepts. So the a value happens to be this other number. It's going to be 0-something. If it's not 0-something, there's another approach we take to get that y-intercept. Now this problem happened to be problem number 11 in your book. And you can see how it's done here. We could go ahead and graph this if we want to. We know it's decay. And if we wanted to, we could make a table and calculate some other values on this. We could put a table together. And let's do that real quick just so we can see how this works. We know that negative 1 produced 6. It told us that in the information. We know that 0 went to 3. And see what's happening is it's dividing by 2 each time, or it's multiplying by 1/2 each time. So I can get some other values here. 1/2 to the 1 power is 1/2, and 1/2 times 3 is 3/2. or 1.5. 1/2 to the 2 is 1/4, so that's 3/4, and 1/2 to the 3 is 1/8. So this is 3/8. So as we see, it does end up approaching the x-axis as an asymptote. All right, let's do another problem here. One more. This is problem number 12 from your book, number 12. And the ordered pair that they give us is 0, -18. And another ordered pair at -2, -2. Now remember, we're going to always take these numbers and stick them into the function here, where the y-intercept has to be 0 something. Well, in this case, this must be a, because it's the y-intercept, 0, -18. Now, I can graph this a little bit just to see what's going on, but I don't need to. 0, -18, well, that's way down here. And -2 is -2. -2 is -2 is right here. So it looks like we've got a decay situation again. It could be. Well, let's go ahead and plug in the numbers. The y value is -2, this one here. And a we see to be -18. And the base we don't know. And x we know to be -2, this one here. Well, let's solve it. We're going to divide by -18. As I said, we're always going to start by dividing by that a value. This is 1/9, and that's equal to b to the -2. Sorry about that glare on the screen there. We'll try to work around it a little bit. That means 1/9 is equal to 1 over b squared. Well, I can see this now, that this has got to be 3 at the bottom here. And notice it can't be -3 because bases, we said the other day, was the bases could not be negative. So I'm going to cross multiply just to see this. B squared equals 9, or b, take the square root of both sides, b has to be 3. So the base is 3. So our equation is y equals the y-intercept, the base is 3, and there's x. All right. Now, oftentimes, these exponential problems have to do with population. Many times it's dealing with population growth. Sometimes the population can grow rather rapidly, and we see that in all kinds of ways with animals or other molds or things like that. Problems 19 and 20, problem 19 and 20 in your book, talks about population growth of rabbits. So I'll read the problem. During the 19th century, rabbits were brought to Australia. Since the rabbits had no natural enemies on the continent, their population increased rapidly. Suppose there were 65,000 rabbits in Australia in 1965 and 2,500,000 in 1867. Write an exponential function that could be used to model the rabbit population. Well, we notice that from the problem, they give us some time. Well, time's got to be x. And it said that in 1865, the population was 65,000 rabbits. And in 1867, just 2 years later, 1867, the population was 2,500,000. Now, this is not, this involves having a time that doesn't actually start with 0. And so we do ourselves a favor here by letting 1865 be equal to 0 and rewrite these two equations, or these two ordered pairs. If 1865 is 0, we'll get this ordered pair. And that means then 1867 would have to be year 2. Now this is a nice way to do the problems, and this is similar to what we did with linear equations. If we let our graph actually start at 0, rather than letting it start at some other distant time in the past. So if we let 1865 be 0, then 2 has to be 2,500,000. And we're going to do that anytime we have time involved in the problem. We're going to let that first year, that initial year, be equal to 0 so that we can take advantage of that y-intercept idea. So let's go ahead and put this in the function. We're going to use these two ordered pairs here now. Well, 0 is 65,000. That means that that's the y-intercept. So we're going to put 65,000 in for A, the y-intercept. And we're going to take the other ordered pair and put it in for x and y respectively. So y is 2,500,000. B we don't know yet, but we do know that x had to be 2 at that point. So now all of these numbers have been plugged in, just like we did before, and we're going to take a minute to... So let's go ahead and solve this just like we did before. We're going to divide both sides by the A value, 65,000. And these go out, of course. This, I did it with a calculator, I've got about 38.5 or so, we'll round it off. 38.46, we'll round it to that. And then we've got it's equal to b squared. Well, in order to get b alone here, we're going to have to take the square root of both sides. Well, the square root of this, I could probably get close in my head. It's a little over 6. But let's go ahead and use the calculator here. So when I take the square root of both sides here, I get about 6.20. We're going to put the 0 there just because we want some accuracy on this. So the base is now 6.20. And so we can write our equation, y equals the initial amount. We'll stick that back in there. And the base is 6.20 raised to the x power. There's your equation. Now this was problems 18 or 19. Problem 20 has you make a calculation with that. Well, let me read that. Problem 20 says, assume that the rabbit population continued to grow at that rate. Estimate the rabbit population in 1872. Well, in 1872, well, that would be 65 is 0. That would be 7 years later. So this ordered pair has got to be 7 something. So we're going to take that 7 and stick it in here for x. And you'd use your calculator to calculate the rabbit population in 1872. And then, again, we're using 7 because that's 7 years after 1865. Remember, 1865 is that time in which we let it be 0. So what happened to the population? Let's take a look what the calculator had to say. Well, using your calculator with the exponent key, you would take 6.20, and you'd raise it to the 7th power, and then you could hit equal here, it doesn't matter actually, and then multiply times 65,000. And what you end up with here is a value in the neighborhood of 23 billion, about 23 billion rabbits. All right, now I'm going to give you a bonus feature here that is not in your book. It is talked about online in places as well. But what if the ordered pairs we end up working with are not, neither one of them is the y-intercept? Let's say 2, I don't know, make it up, maybe 2, 10. And let's say the other ordered pair is, say, well, let's just make it 3, 25, something like this. Neither ordered pair is 0 something. So we don't really have the y-intercept. We can't plug that in here. We have 2 ordered pairs, and we can see that 210 is about here, and and 325s here, so it looks like it's going to be growth of some kind. But we don't have either a y-intercept here. Well, we're going to use the same idea that we used back in solving systems of linear equations. Here's our function, and we're going to write two equations here with two variables. Let's take the first one here. Y is 10. A we don't know. Of course, we don't know the y-intercept. B we don't know. That's the rate. And x is 2. And we write another one. Say is 25 is A, or y, excuse me. A we don't know. And B is 3. Or B is we don't know, and the exponent is 3. Now, in linear equations, we solve this by either the technique called substitution or elimination. And I could use either one here. Just for the fact that we're doing this here today, we'll just go ahead and solve this using elimination. Now, if you remember from algebra, from solving systems, we solved elimination by adding the two equations. Well, I'm not going to add these two equations because the base is actually proportions or ratios. We're actually going to solve this by setting up a proportion. And I already have that proportion here. I'm going to erase that line for adding, and I'm going to make it a line. Excuse me. I'm going to make it a line that's actually a division line. I'm going to put it right in here, like that. I'm going to divide. And I'm actually going to divide these two instead of add them. So here I have the fraction. Let's see, I can reduce that fraction to 2/5. And notice we're going to cancel A over A. Well, A over A, that's what we wanted to do, is to get a variable to eliminate. And this is B squared over B cubed. And now, if we simplify this, we got 2/5 equals, canceling here, I get 1 over B. So let's cross multiply. 2B equals 5, and dividing by 2, we see that the base is 5/2, or 2.5. So it is growth. It's a growth equation. And we eliminated the letter A. Now we have an equation, y equals A, B is 5/2 to the x power. Now we can do like we did in the other one, take either one of these dots up here, it doesn't matter. I think I'll take the 210, put 10 in here. We don't know A, but we do know that x is 2. And we're going to solve this for A. Well, instead of, we can't divide both sides by A, what we're going to do is to go ahead and apply that exponent here. This is 25 over 4. And if we multiply both sides by the reciprocal, 4/25, we end up with 40 over 25 equals A. Now we have the A value. I can reduce this actually. 5 goes into both of those, 8/5. So A is 8/5, and our final equation be y equals, the initial amount is 8/5, or 1 3/5. The base is 5/2, and x. So there's your equation. Now, we have an equation here, and we solved it by using a system. But remember, if you're going to solve a system here, you do it by ratios. Now, we could also solve this equation using substitution. Let's do that. All right, here we have the same equation. And we're going to solve this system to find out what the exponential function is. And we're going to do it this time by substitution. So I'm going to write both of my equations, and this time I'm going to put them next to each other instead of stacking them up. We stack them up when we wanted to use elimination, but we'll put them next to each other if we want to use substitution. So let's start with this first number here. 10, y is 10. A we don't know, we're going to find it. B we don't know, we're going to find that. And x is x is 2. The other equation, y is 25. A we don't know, and neither do we know B, and the exponent is 3. Now, what I'd like to do is solve one of these variables, solve one of these equations for a variable, and then substitute it in. Let's take this one, just because it's just as easy as any other. If I divide both sides by b squared, I will get a alone. That's what I wanted. Now we're going to take this item here, and since a is equal to this, we're going to take it over here and stick it right in there. 25 equals 10 over b squared times b cubed. Right? A is 10 over b squared. Now this one actually looks easier to solve this way. If we reduce, we get 25 equals 10. B cubed over b squared is b. And divide both sides by 10. And we discover once again that b is, see, 5 goes in there, 5 halves. The base is the same. So we found the base the same way. Now we're going to take that and stick that back in just like we did before. And this time the base is 5 halves. Okay, and we're going to stick one of these numbers in. Let's stick the other one in this time, just to make a point here. If this ordered pair is 325, we'll stick 25 in here. A we don't know. X is 3. Well, this might be a little harder because I got a higher exponent here, but let's find out. 5 to the third is 125. 2 to the third is 8. Now if I multiply by the reciprocal, I get 8. This is 25 over 125 reduces. That reduces by 5. 25 goes in the top. 5 goes into the top. 2. 5 goes into the bottom 3. And over here, this is going out completely. So A is equal to 16/3. I just paused it and realized that I had done the arithmetic wrong here. This should have been 8 over 5, not 16/3. So there we go. Now we know A is 8/5. So we'll stick that back in. Y equals 8/5. We don't know B. And I'm sorry, we know B. We do know B. B was 5 halves. So this problem, I'm not sure which one is easier, substitution or elimination, but it just shows you that you can actually solve and find an equation even if you don't have the y-intercept. Now this is a bonus feature for you to be able to do that. All right, so you're ready now to finish the other 2 assignments on page 527 and 528. Here they are again. Notice you're going to be doing problems 11 and 12 again. I just did those for you. And 19 and 20. I'd like you to do those again. Make sure you're pushing the buttons on all of those. So do the best you can. If you have a question, please email me. Go ahead and subscribe if you know how to do that. And then maybe make it easy for you to find all my videos when you need to. Ciao. Have a good day.